Problem today, there were actually two problems. One was to determine the e to the kt form of the function p of t equals 4 times 1.07 to the t. We see that we can immediately let a equal 4, so we have this, and if a equals 4, then e to the kt has to equal 1.07 to the t, so that this part of the function will be equal. So we get 1.07 to the t equals e to the kt. We take the natural log of both sides. The natural log of 1.07 to the t is t times the natural log of 1.07. Natural log of e to the kt, natural log being the inverse function of kt, just gives us kt. T's divide out, and we end up with k equal to the natural log of 1.07, which is approximately 0.0628. So we end up with p of t equals approximately 4 times e to the 0.068t. If we have a situation where we have a growth factor less than 1, this corresponds to exponential decay, whereas the 1.07 was a growth factor of 1.07, so the growth rate was 0.07. This is an exponential increase, exponential growth. This exponential decay situation, we have a growth rate of negative 0.07 and a growth factor of 0.93. Again, we let a equal 4, and e to the kt we set equal to 0.93 to the t, and we solve in exactly the same manner. The natural log of 0.93 is negative 0.073, so that k is going to be negative 0.073, reinforcing the idea that for exponential decay we do get a negative exponent. I didn't write out the final form, but it would be very much like this. When p of t equals 4e, and instead of 0.068t we would have the negative 0.073t. The other part of the quiz gave us the following situation. We have a derivative dy dx equals x squared, giving us the rate of change of y with respect to x. And when x is 2, y is equal to 10. Okay, so we see the rate is your dy dx. So when x equals 2, what is the rate? One of the first questions was, what's the rate when x equals 2? Well, if x equals 2, the rate is going to be 2 squared, or 4. Now, it helps to think about a context. If we think of depth versus time, of course x squared is not a typical rate function for depth versus time, but we might have a different shaped container where this was the rate function. We would think of this as being 4 centimeters per second if y is measured in centimeters and x is the time, clock time in seconds. Okay? Now the question was, if x increases to 2.5, by how much does y change? Well, x is 2, okay? When x is 2, y is 10, and x is going to increase to 2.5. That means that our x increment, our delta x, has got to be 0.5. In order to go from x equals 2 to x equals 2.5, we got delta x equals 2.5. What's our delta y? Well, remember that delta y over delta x is approximately equal to our instantaneous rate. So if we take this as the rate, we're going to get a delta y of, remember the rate is 4, standing for probably 4 centimeters per second, times 0.5, our delta x would correspond to 0.5 seconds. That gives us a delta y of 2. So that at a rate of 4 units per unit of time, over a time interval of 0.5, we end up with a change of 2. So if y starts at 10 and changes by 2, then we get y equals 12, and this is the result we're looking for.